Good morning and welcome back to this video series on control systems. In the past few videos, we have seen that TF transfer function is the ratio of Laplace transform of output to that of input with all zero initial conditions. And we have also seen that TF of a LTI system is characterized by its poles and zeros. After watching this video, you'll perhaps be able to write equations and derive transfer function of simple RLC circuits. There are three components in any general RLC circuit: a resistance, an inductance, and a capacitance. We will try to see each one of them and write physical equation and then try to derive the transfer function of a general RLC circuit. Shown here is a representation of a resistance. A resistance R decides the amount of current flowing through it when subjected to a potential difference. We explicitly indicate time t here to indicate that we are working in time domain. When we are working in Laplace domain, we use capital letter V here, capital letter I here, and within the brackets indicate S to show that we are working in Laplace domain. When several resistances are connected, they may be connected either in series, hooked up one after the other, or they may be connected in parallel. We say that if the same current flows through both the resistances R1 and R2 here, we say that they are connected in series. And we say that the effective resistance of these two R1 and R2 put in series is the sum of these two individual resistances. Remember that same current flows through the resistances that are in series. When they are connected in parallel, the current is split between these two resistances. We say that these resistance R1 and R2 are in parallel when certain current is split between this R1 and R2. I1 goes through R1, I2 goes through R2. When two resistances are connected in parallel, their effective resistance, that is one single resistance which can substitute for this combination of R1 and R2, is obtained from this reciprocal of Re is sum of reciprocals of resistances R1 and R2. Remember that resistances in parallel share the current. Shown here is a representation for inductance in a RLC circuit. In an inductance, the potential drop causes a rate of current, time rate of current. Time rate is indicated by derivative with respect to time. That is, take current I of t, differentiate with respect to time, multiplied by the inductance L, you get the potential drop across the inductor. Again, note that we are explicitly using t to indicate time, lowercase letter for time domain variables. When inductances are connected in series, same current flows through them, and the effective inductance of equivalent inductance of these two put together, L1 and L2 put together, is sum of these individual inductances. In place of this L, we use LE, where LE is the equivalent inductance, that is sum of the inductances. Inductances, when they are connected in parallel, they share the same current. I1 goes through L1, I2 goes through L2, and the equivalent inductance may be obtained as reciprocal of sum of reciprocals. And you need to remember, inductances in parallel share the same current. A capacitance in an RLC circuit is represented by a symbol something like this here. Okay. In a capacitance, the voltage drop across the capacitance is given by integral of the current flowing through this from 0 to t, and then multiplied by 1 over C as shown here. When you connect two capacitances and hook them as shown here one after the other, we say that they are in series, and same current flows through capacitances in series. When you have two capacitances in series, their reciprocals may be summed to find the reciprocal of the effective equivalent capacitance as shown here. Similarly, when capacitances are connected in parallel, current is shared among them. I1 goes through C1, I2 goes through C2, such that I1 plus I2 is I. When capacitances are connected in parallel, you find their equivalent capacitance by summing them up. Remember, capacitances in parallel share the current. Since we deal with Laplace transforms with a view to deriving the transfer function, we write the equations, then take Laplace transforms with zero initial conditions and see what is the contribution of each of these components. If you take Laplace transform of the first equation, in place of this lowercase v, you use uppercase v. Vrs is equal to R times Is, and we have seen that each differentiation in some sense is equivalent to multiplying with s in Laplace domain, again provided initial conditions are 0. Again, Vc is the time domain variable, capital V sub Cs is the Laplace domain, because integration in some sense is equivalent to 1 over s, again with 0 initial conditions. So whenever you see a resistance R in the equations, its contribution is R. When you see an inductance L, its contribution is L times S. When you see a capacitance, its contribution is 1 over C. Now that we have individual component equations, we'll see how we club them into a single equation in a circuit like this. You have a resistance, you have an inductance, and you have a capacitance in series. We see that if VR is the drop across resistance, VL across inductance, and VC across the capacitance, and the total voltage applied across these three elements in series is V of S, we say that this total potential difference is sum of the individual potential differences, and write V of S is R times Is, because we have seen the contribution of a resistance is R, contribution of an inductance is Ls, contribution of a capacitance is 1 over Cs. Having seen this, we can say we can collect all the terms with Is on in one group of parentheses and write that Vs is so and so expression multiplied by I of S, and thus take this Vs onto the right hand side of equal to sign and this whole expression inverted onto the left hand side to write Is over Vs is this expression, and this is the transfer function of this RLC circuit in series. To derive this Laplace transform, see what we did. We wrote individual equations, components describing equations describing components of individual components. VR is equal to Ri, VL is equal to L di by dt, VC is equal to 1 over C integral I. Took Laplace transforms with 0 initial conditions and then derived the transfer function of the system. So we wrote individual equations, then imposed the system level constraint, that is this total Vs is equal to VR plus VL plus Vc. To summarize, we saw that to derive TF of an electric circuit, we write individual equations from physical principles and then impose system level constraints, and then we simplify to obtain the transfer function. You can see that this RLC circuit in series is a second order system because you have an S square present in it. That's all we have for now. Have a great day.